Okay, so we're going to discuss the physics of spin, which in some sense we've been doing already. But we're going to do it using the Stern-Gerlach experiment. Okay. In some sense, the Stern-Gerlach experiment is one of the most quintessentially quantum experiment. Do you guys know about this experiment?
No, sir. I've heard about it, but I haven't went into it properly.
Okay, so let me explain the setup. But of course, as you have guessed, that in discussing quantum mechanics, we always refer back to classical mechanics. It seems like quantum mechanics, as it stands today, cannot really be formulated without classical intuition, which is kind of a strange thing because we expect, at the end of the day, classical physics to emerge from a more fundamental version of reality, which should be given by quantum mechanics. But we are classical creatures, so a lot of our intuition about the physical world comes from classical mechanics. And so we still rely a lot on classical mechanics. So classically, we can associate a dipole moment to a current loop, right? So if I have, say, a little current, which has, it's a loop of current, so there's a battery, so a battery and a little loop, then we can associate with this a magnetic field, right? And therefore we can associate with it a magnetic moment. So it's like a little magnet. So there is some magnetic moment associated with it. So in the quantum realm, charged particles with non-zero spin have magnetic moments. Associated with them. And if you think about it a little, it does make sense because, what is a classical picture of a charged particle? A classical picture of a charged particle is some sort of very tiny, say, sphere, right? Which has some charge distribution on it, right? So this is not an accurate picture, but it's some sort of, suppose you take a sphere with some distribution of charges on it, and you set the sphere spinning, right? So if you set the sphere spinning, then you will have a small amount of current, going on the sphere, and therefore, because there'll be small currents, the sphere will have a magnetic field and therefore a magnetic dipole associated to it. Okay, so in some sense, spin, a spin is a kind of angular momentum, so it is a kind of rotation, and we have some, because it's a charged particle, we can associate some magnetic moment to it. Okay, so this is not a proof, but this is just a motivation. Does that make sense? Do you see what I'm trying to say?
Yes, sir.
So what is interesting is that in the quantum world, Kali agrees, in the quantum world, even uncharged particles such as the neutron, have magnetic moments. And you might say, why is that? Because, we don't associate classically a magnetic field when there is no current in the loop. So if I stop the current in this loop, the magnetic field will go away. What this kind of points to is that the neutron is not a fundamental particle. And it is made out of charged particles. I'm very sorry, called quarks. Which have spin. Okay. Okay, so that's why even particles such as neutrons will have magnetic moment. So the Stern-Gerlach experiment was originally done with silver atoms. Okay. And silver atoms do have their spin half particles. Okay. Okay. So what is the experiment? Okay. So what Stern and Gerlac did is that they sent a beam of spin half particles sorry, let me just Chaka, can you take care of your brother? Sorry, it's a very can you give me 1 minute? I'm gonna take the kitten and put it in the other room. Chalo. All right, kitten has been locked in the other room. Okay, so what Stern and Gerlach did is that they took a beam of spin half particles and sent it through an inhomogeneous magnetic field. Okay, so this is kind of a genius move. So how did they create such an inhomogeneous magnetic field? Well, they took two magnets, one with a very sharp north pole. So the geometry of the magnet is such that the north pole has this very sharp edge, knife edge, while the south pole has a blunt thing. So they brought these two magnets together, and then what happens is that the magnetic field line, just from geometry, is, we know that magnetic field lines, will basically will do stuff like that. So you can see that in that region, the density of the magnetic field line is higher than in this region, right? And therefore, the magnetic field is more intense near the North Pole than near the South Pole. So that means that as you go up, the magnetic field, the strength of the magnetic field is increasing. And therefore, it's an inhomogeneous magnetic field. Okay? So classically, what is the energy of a small magnetic moment in such a magnetic field? Well, its energy is classically given by minus the dot product between the magnetic moment and the magnetic field. So this minus sign ensures that when the magnetic moment is parallel to the magnetic field, the energy is lower than when the magnetic moment is anti-parallel to the magnetic field. So this is the magnetic field, and this is the magnetic moment. Okay, so because when they're anti-parallel, the dot product gives a minus sign, and therefore this becomes positive. When they're parallel, then the dot product gives you a plus sign, so it remains negative. So the delta E between the two states at a given point in space will be 2 mu b, right? Where the or you can see E plus is mu b and E minus is minus mu b. Okay, the two energy, the high energy and the low energy. Okay. Oh, this is classical. So these are the these are the extreme values. Okay, any questions?
No, sir.
Okay, so now the magnetic moment of the particle is given by, now this is something that we cannot derive here. You just have to take it on trust. We have to go to the Gerlac equation to derive this. Is proportional to, at least, I'll try to think of a way to motivate this. The magnetic moment is proportional to the spin. And we have chosen the unit such that this is, the coefficient is 2 mu. Okay, so the mu is not necessarily it's not necessarily, well, it is kind of the, the modulus of this. Okay, so now our, classically, our, well, what is going to be the Hamiltonian? So quantum mechanically, we are talking, the Hamiltonian of our system is going to be minus 2 mu b times, because our magnetic field, we are looking at the z component of the magnetic field, times sz. Okay, this is our Hamiltonian. So it's a 2x2 matrix. But classically, what is we want to know what are the forces on the spin up state as opposed to the spin down state. Again, we appeal to our classical intuition. And according to our classical intuition, the force on an object is given by how its energy changes as the gradient of the energy, the potential energy. Here it's the same as the energy. So we see that the plus state is going to feel a force towards the increasing B field. Okay. Toward the increasing B field. Okay. And how did I figure that out? I took this expression for energy and then I plugged it in, and then these two minus signs became a plus sign. I got a 2 mu. S of Z is some constant, and del B by del Z. Okay. So if S of Z is positive, then it's going to feel a force in the positive gradient direction, and if it's negative, it's going to feel a force in the negative gradient direction. Okay? And then the spin, the negative spin down state, it's going to feel a force towards the towards the decreasing magnetic field. Do you agree? It's very quiet out there.
Decreasing magnetic field as in towards the south field,
Yeah,
or
yeah.
like
Yeah.
where
Towards
where the density is lower.
Yeah, where the
Yeah.
magnetic field. Yeah. Okay.
Mhm. Yeah.
Right. So so thus what we are going to observe is that if we send our, so suppose we have an oven here, in which we are heating up silver atoms and giving them some sort of kinetic energy. So the silver atom is being spewed out like that, and here we have some sort of collimator. Okay, so we have some collimator. So this is and what it does is that it collimates the beam so that the beam going out has a very nice direction. And then what happens is that it comes across this Stern-Gerlach magnet. Okay, so this is the North Pole and this is the South Pole. And then the particles which are in spin up state, they get pulled up in that direction. And the particles which are in the spin down state, they get pulled down in that direction. Okay, so as a result of the Stern-Gerlach magnet, we get two beams. So as a result, we get two beams coming out of the magnet. The upper beam consists of particles in the spin up state, and while the lower beam consists of particles in the spin down state. Okay, so we expect the oven to be quite democratic in spewing out its particles. So we expect half of the particles to go in the upper direction, right? And half of the particles to go in the lower direction. Do you agree with that?
Yeah, that's what I thought, but I think I thought wrong.
No, you didn't think wrong. But now I have another question. What if these particles were not quantum particles, but classical particles with some magnetic moment? What would have been the expectation? Would you have gotten two beams, clearly defined beams?
I think so.
Why?
Because we could still have a magnetic moment associated with them. So,
Exactly. But why would you get two beams?
oh, because they would point towards opposite direction, the two magnetic moments, since it's coming out of an oven. So I would assume it to be randomized, probably.
So, stuff coming out of the oven should be randomized. So the magnetic moments here should be in all directions, right?
Yes, sir.
So if it was a classical particle, the magnetic moments would be in arbitrary directions, right? So the dot product here, the dot product here, the cosine angle would be arbitrarily, distributed over a sphere, right?
Yes, sir.
So, some of these magnets will have orientations like that. They will not feel the same force as magnets which are oriented like that, magnetic moments oriented like that. So, and like this. So, the magnetic force on this guy would be more than the magnetic force on this guy, right? And this guy will be more than this. So classically, the force that you're going to that these moments are going that magnetic moments will feel will be on a wide range, and therefore classically you should not get such these two beams, but you should get something that is more continuous. Okay. The classical expectation is that if you catch the particles on some screen, you're going to get something like this. But quantum mechanically, what happens is that you get very two clearly defined beams, okay? Where these particles consist most entirely of spin-off particles and these spin-down particles, okay? So the fact that we have two beams is a result of the fact that we are doing quantum mechanics and not classical mechanics.